Hi everyone. If you insert a row into a Postgres table, could you go find it on disk? The actual file, the actual bytes? That's what we are going to do today. We are going to insert some data and then find it on disk. But before we jump into the terminal, let's first build a conceptual understanding of how Postgres organizes storage on disk. So when we go looking for the data, we'll know what we are looking at. Whatever data we store in Postgres, we store it in tables, and the tables are stored in some files. We call these files segment files. Each segment file has a maximum size of 1 GB, although this is configurable. So if your table grows beyond 1 GB, for the next 1 GB, Postgres will create another segment file. Then for the next 1 GB, it will create another segment file and so on. We can see these files in our file system. Each segment file is made of one or more pages. Let's zoom in to see what these pages actually look like. These pages have a fixed size of 8 KB. Pages are the smallest unit of I/O. When Postgres reads from or writes to a segment file, it's reading or writing 8 KB of data at a time. Any change, no matter how small or large, has to happen through these pages. Each page has some headers followed by line pointers, which grow from the top of the page. The actual tuple data grows from the bottom of the page. The line pointers point to the tuples. For example, let's say that the first tuple here starts at the offset of byte 8152. Then the first line pointer is going to point to this offset of 8152. Each tuple also has some headers like transaction IDs or some flags, maybe a null bitmap, followed by the actual values. The space between the line pointer and the tuples is called the free space. This is where the new inserts actually go. There's also a special space at the bottom of the page which is used by indexes, and it's not really relevant for us now. At this point, I think we need to ask one important question. Why do we even need these line pointers? Why can't we directly start storing the tuples from the start of the page? We'll talk a bit more on this when we talk about indexes, but for now, let's assume that we don't have the line pointer array. Let's assume that the tuples grow from the start of the page. And imagine the row 3 from this page is deleted. We will now end up with a fragmented free space, which is not ideal. So we would want to move these tuples around to avoid fragmentation. But we can't directly move them because there could be indexes or some other data structures that point to these tuples. That's why we need the line pointer array. It lets us reorganize the page to better utilize storage. Sometimes these are called slotted pages because there's a slot for each tuple stored in the page. To summarize, Postgres stores data of a table in segment files. Each segment file is made of one or more pages. Inside each page, there are some headers followed by line pointers. These pointers grow from the top of the page. The actual tuple data grows from the bottom of the page, and the new inserts go in the free space in between. So yeah, that's it. Let's now jump into the terminal. We'll use the same Docker container that we used in the last video. I'll link the Docker file in the description. Let's log into the container and explore the file system a little bit. Since we are running Postgres in this container, there must be some files or directories that Postgres is storing to save the data. Generally, there is an environment variable called pgdata that stores the path to this storage. If not this variable, the storage location will be mentioned in some configuration files. Let's see where Postgres is storing data inside this container. Here, Postgres is going to store data in this data directory. If we change into this directory and list the contents of this, we see several subdirectories and some configuration files. Some of these directories handle the replication, some handle the write-ahead logging, while some handle the snapshotting. For now, we are interested in this base directory. This is the default directory where all the databases, the tables, the metadata, the indexes, everything is stored. If we change into this directory and list the contents, we see a bunch of numbers. These are called the object identifiers. Object identifiers or OIDs are the primary keys that Postgres keeps for its own internal system tables. For each database that we have, Postgres will create a subdirectory in this base directory. Let's now create a database and let's see this live. What I'm going to do now is I'm going to split my terminal into two panes so that we can run PSQL commands without having to switch back and forth between terminals. Using PSQL, let's now create a dummy database. And we can use the Postgres system tables to find out the object ID for our dummy database. There's this system table called PG database, which can give us this information. Here we can see that our dummy database has an object ID of 16438. Based on what we know so far, we would expect that Postgres would have created a subdirectory named 16438 under the base directory. Let's verify this by listing the contents of the base directory. It looks like Postgres did create this directory for us. Now we can change into this directory and list its contents. Remember, this is a freshly created database, but already there are a couple of hundred files in this subdirectory. These are all the system catalog tables which are copied into every database in Postgres. Let me clear up both the panes now and let's create a table in this database and insert some data. Let's switch to this dummy database first and let's now create a simple users table. Each user will have an ID, a name, and an age. Let's now insert a row in this table. Now, in this 16438 directory, there are going to be a few more files that would have been created when we created this table and inserted the row. It's time to go data hunting now. Let's find a file where this row would have been inserted. These will be the segment files that we saw at the start of the video. We can again use Postgres system tables for this. The relation file path table gives us this information. For example, here, all the data for our users table is in this segment file 16449. This is where all the tuples that we insert, all the data that we insert is actually going to be stored. Let's verify this. Here we see a file named 16449, which is of exactly sized 8 KB. Even though we inserted only a single row, the file is still 8 KB in size. Remember that the unit of I/O is one page, which is generally 8 KB in size. So even if we wrote a single row, we still got 8 KB of data on disk. Now let's actually start peeking into this file and interpreting the raw bytes. Let me quickly clear both the panes again. Actually, we don't need the PSQL pane anymore, so let me just exit out of it. We'll now start interpreting the raw bytes on disk. Frankly speaking, nobody really needs to do this, but I think it's awesome to do it once. As we saw before, this 16449 file consists of one page of size 8 KB. Each page has some headers, then line pointers, followed by free space, and then the actual tuple data. We can dump all the raw bytes on this file using XXD. Here, if we scroll to the top of the output, we see that there are some non-zero bytes, followed by a bunch of 0 bytes, and at the end of the page, or at the end of the file, there are again some non-zero bytes. This loosely confirms the structure of the page that we have in mind. To interpret these bytes, we are going to look into Postgres source code, because at the end of the day, the page headers, the line pointers, and the tuple data are going to be some structs in C, right? So if we look at these structs, we'll be able to interpret these bytes. Let's first look at the page headers. We are in this file called buffpage.h in the Postgres source code, and in that we can find the struct defined for page headers. This is what defines the page headers. The first 64 bits or 8 bytes are for the last LSN. We'll look at LSNs a lot later. For now, it's just a 64-bit number that we assume is just there. After that, we have two 16-bit numbers for the checksum of the page and some flag bits. Then we have three interesting offsets: the start of the free space, the end of the free space, and the start of the special space. All three of these are 16-bit numbers again. Then we have a couple of more numbers for the transaction ID and the page version, followed by the line pointer array, which is again considered to be part of the page header itself. Except the line pointer array, these other numbers make up the first 24 bytes of a page. Now we can go to the terminal and try to interpret the first 24 bytes of our page. Back in the terminal, we can again use the xxd utility to print out the first 24 bytes in binary. Here, on the left hand side is the offset in the file. On the right, we have an attempt by the shell to interpret those bytes, and in the middle, we have the raw bytes themselves. The first 8 bytes here correspond to the LSN, which we are going to skip for now. Then we have two 16-bit numbers for the checksum and the flags. Both of them are set to 0 in our case. So now let's try to interpret the PD lower and the PD upper offsets to get the start and end of the free space. We'll use a bash utility to convert binary into decimal. And one thing to note here in this output is that these numbers are stored in little endian format. I'm not fully sure of how the endianness thing works, so I'm guessing that you might see a different output than this depending on your machine, and you may want to check this with an LLM perhaps. But here in the little endian scheme, the most significant bytes start from the right. The bits themselves are not reversed, but the bytes are. So when we are interpreting these bytes, we have to reverse the bytes. Let's now interpret the first 16-bit number, which is for the start of the free space. We'll be using the BC utility for this. To interpret this number, we'll take the rightmost 8-bit first. Then we'll take the previous 8 bits. And this corresponds to the start of the free space. So at the offset of byte 28 in our page, the free space begins. Or in other words, it is the offset where the line pointer array ends. Similarly, we can interpret the next 16 bits as well. So we can use the same BC utility for this. And again, we can take the rightmost 8 bits and we can take the previous 8 bits then. Now this corresponds to the end of the free space, or in other words, at the offset of 8152 is where the tuple data starts. And since our page is not an index page, the next 16 bits, which are for the offset of the special space, will be set to the offset of 8192, which is the end of the page, right? To signify that there is no special space here. If we want, we can repeat this process to interpret the version number or the transaction ID, but we'll skip it for now and go directly to the line pointers. The line pointers are again some structs in the Postgres source code. Remember, each line pointer points to the actual tuple data in the page, right? The item ID data struct is defined in this header file called itemid.h. It's a very simple struct containing only 3 fields: the offset to the tuple, some flag bits, and the length of the tuple. Each line pointer is of size 32 bits or 4 bytes and contains these 3 fields. So in our page, we have the first 24 bytes for the page headers. Then we have 4 bytes for every line pointer. In our case, we just have one line pointer. So if we read the bytes 25 to 28, we should be able to see and interpret the line pointer. We can again use the xxd utility to skip the first 24 bytes and read the next 4. So let me first clear up the pane first. Now let's try to read the 4 bytes corresponding to the line pointer. Now here's where things can be slightly confusing. The numbers are laid out in little endian format, and we want to extract 15 bits from the first 16 bits. So which 15 bits should we be taking? We need to think of the first 2 bytes as a 16-bit number. In that, the bits are read from right to left. So we'll be taking all the 8 bits from the first byte, and we'll be taking the lower 7 bits from the second byte. So let's see how that goes. We can again use the BC utility for this. And as we said, we'll be taking the lower 7 bits from the second byte and the 8 bits from the first byte. And because it's little endian ordering, we have to flip them. So we'll first take the lower 7 bits and then we'll take the 8 bits. So this gives us the offset for the start of the tuple. At the offset of 8152 in our page, the tuple that we inserted will start. Now we want to identify the next 2 bits for the flags, right? At this point, we have already read 15 bits from the line pointer. So naturally, the next 1 bit will be this unused bit, and the other is the lowest bit in this third byte. And again, because of the little endian ordering, we need to flip them. So this is how it will look like. So we'll be taking the last bit from this third byte, and we'll be taking the first bit, which was the unused bit, in the second byte. So the flag value is 1. Now getting the length of the tuple is simpler. We just have to take the remaining 15 bits, organize them according to their little endian ordering, and we get the length of the tuple. Right? So we can organize, right? So again, we can use this BC utility. So as per the little endian ordering, the last 8 bits will go first. Then the higher 7 bits will go next. And we get the length of the tuple. So what this means is at the offset of 8152 in our page, we have a tuple of length 36 bytes. Now let's look at the actual tuple data. We won't go into as much details here, but we'll try to quickly get a high level view. The tuple that we inserted was a user Bob with age of 25. And we know that the tuple starts at the offset of 8152 and has the length of 36 bytes. Again, we can use xxd to get these 36 bytes. Now for tuple data as well, there are some headers. They span the first 24 bytes and they're mostly related to transaction IDs and bit masks. You can find them in the Postgres source code. I'll link it in the description, or you can use any LLM for this. After these first 24 bytes, the remaining 12 bytes are the actual tuple data. So again, we can use xxd to get these 12 bytes. These are the actual values of the row that we inserted. Here, the first 4 bytes give us the ID of the user. Again, this is little endian ordering. So if we rearrange it, we get the ID as 1. Now shell here has already tried to interpret the next 4 bytes as the name of the user, which we can see here on the right. And lastly, if we try to interpret the last 4 bytes in little endian ordering, again using the utility BC, we get the age of Bob as 25, just what we inserted. All this byte level interpretation is highly tedious to do manually, but there are extensions that do this for us. We can use something like pg file dump or page inspect to quickly get these values. Okay, so we've looked into a lot of details of how Postgres organizes storage. Let's summarize this at a high level. Postgres stores all the data for a table in segment files. Segment files are made of one or more pages, and the page is the fundamental unit of I/O in Postgres. Each page consists of page headers, free space, and the actual tuple data. Whenever we try to insert some data, Postgres will first find a page with enough free space. If there is no such page, Postgres will create a new page in the current segment file. The new page will be created in the same segment file till the max size of the segment file is reached. Once there, a new segment file will be created and this process will repeat. So that's all for this video. I hope you all found this interesting, and I'll see you in the next video.